Hello everyone, and welcome to the talk on Advanced Left Shift ESL Technologies by CircuitSutra. So I think you can start. Yeah, you can start now. Sorry for the delay.
That's okay. So good evening, everyone. So can you see my screen?
Yeah, it's visible.
Okay, fine, sure. Yeah, so welcome to today's session. My name is Umesh Sisodia. I am founder and CEO of CircuitSutra Technologies. And the topic for today's session is transforming semiconductor design using advanced shift left ESL methodologies. In today's session, like we have 4 presentations. And after every presentation, we can take few questions. If you have any questions, so you can note it down. And at the end of presentations, we can take few questions. And later in the end, we can take more questions. So before we go into details of ESL, let's see what are some major trends happening in the semiconductor industry. So one of the trend is the evolution of the semiconductor manufacturing process. So as we know, inside a semiconductor chip, the fundamental smallest unit is a transistor. So as the semiconductor manufacturing has been advancing in the last few decades, there are two parameters related to transistor that has been continuously changing. So one is the size of transistor that has been continuously reducing over the period of time. And second is the number of transistors that can be fabricated inside a single chip. So that has been increasing continuously. So there is a very famous law in our industry, which is Moore's law. So it was given by Gordon Moore in 1965. Gordon Moore is the co-founder of Intel. So in 1965, he gave a statement that number of transistors that can be fabricated in a single chip or in a given unit of space will double every 2 years. And the cost of computing will become half in that particular duration. So, since then, the industry has seen this trend that this law actually holds. So in 1965, when this statement was given, at that time, only 50 transistors could have been economically fabricated inside a single chip. But if we see today in the latest SoCs, the latest SoCs can have the number of transistors which can be more than even 6 billion or so. So in 1965, when Gordon Moore have given that statement, there was no concept of this technology node in the manufacturing of semiconductor chips. So as the process advanced further, so there were different technology nodes that came one after the other. So like in 1971, the process was the 10 micron process, and then till 2012, it actually got reduced to 22 nanometer kind of thing. And today we are talking about something about 10 nanometer or 7 nanometer. So as the process advanced and the transistor size kept on reducing, the number of transistors that goes into the chip that actually kept on increasing. The impact of that evolution of semiconductor manufacturing can be very visibly seen in the evolution of microprocessors actually, which have been at the heart of the semiconductor industry. So like in 1971, we had the first commercially produced microprocessor, which was Intel 4004. So it was fabricated at a technology node of 10 micron, and the number of transistors which it had was around 2300. If we see the latest one, which is again produced by Intel, Elder Lake in 2021. So it is Intel 12th generation core, and it is manufactured at a technology node of 10 nanometer. So we can see a scaling of around 1000 times in the size of the transistor, and the number of transistors it is in billions actually. So microprocessor invention, that was one of a very significant milestone in the industry, because that's when actually there could be a software which could run on top of microprocessor. So since that time, any electronic product which has a microprocessor, it will not just have the hardware, it will be a combination of hardware plus software. And if we see today, we actually have the systems, the complete systems on the chips. So that was the evolution of the semiconductor manufacturing and its impact. But in parallel, there have been an evolution happening in the chip design methodology as well. I mean, majorly, this evolution has been in the terms of like raising the abstraction of chip design, so that the complexities can be reduced for the chip designer. So like if we see how the chips were being designed prior to 1980s, I mean, at that time, when the number of transistors in a chip were maybe a few thousand or so, so it was fine that, I mean, the designers could manually design the circuits using discrete components like transistors, diodes, etc. And they can create a circuit, and they can use the tools like circuit simulation or polygon level layout tools, and that polygons further go for the fabrication. But as the number of like transistors kept on increasing, so it became more and more, I mean, difficult to design the chips manually in that way by designing the circuit. So there was a need to raise the abstraction further. So in 1980s, we saw this new abstraction, which is like designing at the gate level. Instead of designing at the transistor level, now, I mean, designer used to design using at the gate level, and there were new kind of like EDA tools for the gate level sign off, etc. But the complexity further kept on increasing, and the number of transistors kept on increasing further. So later in 1990s, we have seen uh, that industry actually started shifting to the new abstraction level, which was the RTL, using the language like Verilog and VHDL. And at that time, actually, we start seeing a new generation of EDA tools like simulation, synthesis, place and route, etc. Now, this RTL based flow have been in use since then, and still it is being used, but the complexity have been continuously increasing. So, industry very clearly felt that RTL alone is not sufficient actually to meet the complexities of today's chips. So around mid 2000, the transition to the new kind of methodologies actually started, and that is still evolving. So these methodologies are known as electronic system level methodologies, and that will be the focus of our session today. So these are the advanced methodologies which actually implement the shift left kind of concepts in the industry. I mean, it's not a single kind of activity or single concept which just raises the abstraction. It's a combination of several methodologies, combination of several techniques. But in general, most of these techniques can be broadly categorized into two categories. One is like hardware, software, co-design and co-verification. Because now it's not just designing of the hardware or designing of the chip. We have to take care designing of the software and hardware together. And second category will be raising the abstraction of chip design above the RTL. And these methodologies are implemented using the high level languages like C, C++, System C, Python, UPF, IPXACT, portable stimulus, etc. And as I told, I mean, these methodologies are not replacing the traditional flow, RTL to GDS flow. So that exists, but these augments it further actually. And these methodologies allow us to do several activities which are not feasible in the traditional flow. For example, we can do pre-silicon firmware development. We can automate the regression testing of firmware. We can do architecture analysis. We can do high-level synthesis. And most importantly, we can simulate the complete SoC, or we can simulate the complete system actually very fast. I mean, if we try to simulate a system or a SoC in the Verilog, then it will be extremely slow. I mean, just for simulating, let's say 1 minute of a real time, it might take 1 week or even more than that. But these methodologies actually allow us to simulate a complete system or complete SoC at a very fast speed. And using these methodologies, it's possible to like reduce the cost, reduce time to market, or optimize your chip for specific constraints like power, performance area, etc. So, so CircuitSutra, so we started this company in 2005, which is long back, more than 15 years back. So we started with an aim to define the next generation methodologies, like which have the potential to transform the semiconductor design or potential to transform the electronic system design altogether. And our objective was to emerge as a global leader in whatever, whatever like offerings we provide. So ESL methodologies at that time were just starting up. That was the time when industry was feeling a need that RTL based flows are not sufficient for designing further more complex and more advanced chips. So when we do some exploration, we found that ESL methodologies are the one which actually qualifies the criteria in which we can build a very big company and in which we can also become a global leader. So we have the offices in India like Noida, Bangalore, and one office in US in Santa Clara. We have been focusing in this domain for more than 15 years. We also started an international conference here, India Systems Users Group Conference, which was started in 2012, and it was attended by more than 200 international delegates. And later it was merged with a bigger conference, which is DVCon India in 2014. Accelera Systems Initiative, so it's an international standards body, which is actually defining new standards in the ESL domain. So CircuitSutra got awarded by them. So we got recognized for driving these standards in the Indian ecosystem. And in addition to that, we got several other awards and recognition on this journey. So today, if we see like CircuitSutra has a very strong market positioning. So our mission is to accelerate the adoption of these advanced ESL methodologies in the industry. It mainly consists of three broad components like virtual prototyping, architecture modeling, and high-level synthesis, which we will be talking about in the subsequent presentations. So today, perhaps like we are the only company which is 100% focused on this ESL domain and which understand all the aspects of this ESL domain. So ESL as a domain, I would say is a very promising career proposition. This is the only space in the semiconductor industry where the maximum innovation is happening today and which is actually adding the maximum value to the semiconductors today. So if anyone want to build a career in this domain, before you can get started with the ESL, the fundamental skills that you need to have, it requires a very unique skills, which is a combination of computer science and semiconductors. So like on one side, you have to be very good in like C, C++, Python, object-oriented programming, data structures, algorithms, optimizing the algorithms, computer architecture. On the other side, you also need to have a thorough understanding of the like system on chip architectures, which will include like CPU architectures. So like latest CPUs, we have RISC-V, ARM, a very good understanding of memory architectures used in the SoCs, interrupt handling, etc. The bus protocols, network on chip, or the chip interfaces like UART, SPI, etc. And the understanding of the digital design. It will also help if you have the exposure to SDL and simulations, etc. Yeah, so if you want to keep yourself updated with the latest trends in the ESL domain, you can follow CircuitSutra on the social media. So these are our social media pages. So we keep on updating, posting the articles, latest articles, and latest trends in the ESL domain on these pages. Yeah, so that's all I have in my presentation. So before we move to the next one, maybe if someone have any questions, so we can take up those. So if anyone have any questions, so maybe you can turn on your mic or turn on your camera and maybe you can ask the question. Let me see how do I stop sharing it.
Sir, how can one start learning these skills?
1 minute. So I'm just seeing how do I stop sharing it? 1 minute. It's still in the sharing mode. Is there some?
I think you have to go to Teams and stop sharing. In Teams, you have to stop sharing. There's of Teams, open that and then stop sharing.
Okay, okay, yes. Yes, so can you please repeat the question?
Sir, I had a query that how can one start preparing for these things? Like we are a student currently for electronics engineering, and what are the steps should we take to start learning and get a job in this field?
So first of all, as I told, I mean, it requires a skill which is hybrid of computer science and semiconductors. So very few people in the industry have actually these skills, which are a combination of these two things. So as a student, what I would say is like, so are you from the electronics background or computer science?
So electronics.
Okay, yeah. So I would suggest that maybe, I mean, right in your second year or third year, I mean, you should start learning about these programming languages like C, C++, gain a strong expertise in that. And the other thing that you should start learning is more about like system on chip, microprocessors, latest trends in CPUs, SoC architecture, etc. So you can find lots of information on the net. And still, if you face any problem, you can actually drop a mail to us and we can actually guide you further. We can provide you some pointers how to get started on these and how to acquire these fundamental skills.
Okay, sir. Thank you.
Any other questions we have? Okay, then we can move to the next presentation by Aravinda and we can take more questions in the end. So Aravinda, maybe you can share your screen and
Okay. Yeah. Thanks, Umesh. Thanks for the nice introduction. I have already
yes,
I
yes,
started sharing. Yeah. Okay.
yes, it's visible here.
Okay. Yeah. Thank you. Yeah. So this is my name is Aravinda Thimmapuram. I would be talking about this architecture exploration topic. Yeah. So yeah. So Umesh has already introduced this in his slides that one of the pillars of the ESL is the architecture exploration. In the next few slides, we will go in bit more detail to understand what is architecture analysis and why do we really need it and what are the focal areas there and how do we really use it in a typical SoC. Yeah, so that's the agenda. So what is architecture analysis, right? So if you are looking at designing of any IP or a system, right? So what I mean by an IP is it could be a component like a microcontroller, microprocessors, caches, buses, or memory, or any of them, or it could be a combination, a complete system, which is a combination of these complex IPs together. So that is the product. So when we set out to design this product, so we obviously have certain product features in mind, and with these features in mind, we will design this product. Yeah. So when we realize this product, I mean, using all the different steps of the semiconductor, like the design, fabrication, and finally we get the chip. Yeah, and we start using it here. And when we look at what the realized product features are, right? So here many times we see that it is not really matching to the features that we initially set out to, right? We started off saying, okay, we want this chip to solve this problem. It should have this kind of bandwidth, or it should kind of this kind of a performance at this power point, right? But when you see the final chip, this may not really meet that. Yeah. So so that is when I mean, so let's look at why we really have this mismatch, right? So the reason why there are many reasons why there could be a mismatch in the expectation versus the finally realized product. So one of them is the complex IP system architecture. So the kind of systems and the IPs, Umesh already mentioned the number of transistors, the density of that, and the functionality that's being implemented. And many of you coming from the electronics background, you know how complex the latest microcontroller architectures are, or the cache architectures are. So when you are designing that, and it's completely purely a kind of a paper-based design, you're just designing thing. You don't know finally how this is going to end up realized. So this complexity is one of the main reasons where there could be a mismatch. So you thought, okay, you designed it that will perform like this, but at the end it may not really work out like that. And also the second point is it's very difficult to foresee the interplay of the inputs and the architecture. So you don't know what the real life inputs are, and when you get that inputs, how the architecture choice that we made, how was this going to respond, and what would be the end result? It's very difficult. And so the point here is if we are starting and doing a paper-based design and we kind of mentally calculating things, it's very difficult to predict the real output considering the complexity in terms of the design and complexity in terms of the kind of inputs that are going to come in. Yeah, if at all we even get it right, it could be suboptimal. So what I mean is we have kind of designed this with a lot of buffers. We have designed with a lot of more power consumptions. So at the end, it may still work, but it may not be really the optimal product at the end. Yeah. So these are the reasons for the mismatch. So what are the results of this mismatch, right? So the results of mismatch could be a costly rework. So we realize, okay, now, no, it's not meeting this. We go back to the design, we restart and kind of rework those parts of the design, come back. And this whole process could be really very, very expensive. Yeah. Or in the worst case, the product could fail because the kind of a window, the product window offers is very limited. So if we are late, our competitor could go in much earlier than us or with better features. So we may entirely miss the whole product window and it could completely fail. Yeah. So that's the reason why, I mean, I'm just trying to highlight the complexities. And if we don't, I mean, if you are just doing paper-based designs, I mean, this could at sometimes be very catastrophic. Yeah. What is the solution then? So how do we really solve this problem? Yeah. So the solution to this problem is what we call as architecture simulation and analysis. So basically the idea is you simulate it before you really realize the system. So the basic idea here is you simulate the IP or the system before we actually implement it in the silicon. Yeah. So the concept, I mean, you might be already familiar that in the if a pilot wants to get trained in the in flying the aircraft, I mean, he won't get initially. I mean, he won't directly go and start training on a real life aircraft, right? So he will get a simulation model first, and he will sit and he will work on that simulated model. Will become familiar like what are the controls, and if he presses a control wrongly, what is going to happen. He will get just first start with the simulation model. Another example could be if you are building a house. I mean, there are a lot of such CAD simulation models where you simulate the house in this software before you show it to the client, showing okay, this is how the end results would be. And once you kind of play with that and kind of refine the design, then the end product is likely to meet the goals much better. Yeah, very similarly, in the semiconductor domain, the architecture simulation means you kind of simulate the IP or the system before you go into the implementation of the silicon. Yeah, and you build the simulated model, experiment with different inputs and see what is the output. Is it really matching? If not, then go back, refine it, and kind of evolve the model to an extent that where you are really confident that this, when realized in silicon, is going to really meet the requirements. Yeah. So yeah, and also, I mean, we now have, since we have a good model, we can kind of create an optimal design, right? I mean, we don't have to keep a very long buffer depth, or we don't have to kind of design for a very worst case scenarios. We can kind of realistically look at the inputs and kind of play around with different parameters and then design a very optimal system. Yeah, so this is what is the basic premise of architecture simulation. So what would be the end result? So there's a very good chance of getting the product first time right, because we have kind of factored in a lot of inputs. We have played around with this. Yeah, and then also the solution is likely to be more optimal. Yeah. So yeah, what are the focal areas of this analysis, right? So one is, of course, the performance analysis. That what I mean by performance is whether it's giving the required bandwidth. So if you're just an example could be if you're designing some image processing related things, is it providing a proper image compressions, whether there are blurs and whether there are flickers in it. So this is basically the performance analysis. And then power consumption, is the power consumption within limit, or how long does this, if one charge, how long this is going to last? Like, I mean, with the mobiles, we are all aware, right? So power is very important. If you keep requiring frequent charging, then it's not really useful. So power consumption is very important, right? And then the area analysis. So what it means is all these features, I mean, what's the optimal area? I mean, otherwise, if we are not optimally using it, the silicon area and the cost are proportionate. Yeah, I mean, we will end up creating a product which is very, very expensive for the target use case. Yeah? So these are the few key important focal areas of the analysis. Yeah. Let's look at a typical system on chip and look at some of the parameters. What are, I mean, I've been very abstract so far. Let's try to make it more grounded and see, I mean, what are the kind of parameters that the architects look at and how do they optimize. So in this system on chip, I'm just considering the important components here, what we call as the critical path. The CPU here, the microcontroller, microprocessors, the caches, yeah, the interconnect and the memory. Yeah, typically this is the path that is exercised very heavily and the performance really matters. So if you are trying to analyze this kind of a setup, then for CPU, I mean, you would look at parameters like pipeline depth, what is the pipeline of the CPU, the branch prediction, you will look at whether how is my branch prediction algorithm, is this the best and stuff like that. And like for cache, for example, it could be cache policy, the line size, the replacement policies, what kind of replacement policies we have, and how is it going to impact the overall thing. Yeah. And then if you're looking at interconnect, it could be the queue depth, the arbitration, the address maps. So you can play around with the address map to see whether this is addressing everything. Yeah. And then when you come to the memory, it's again the queue depth, the bank arbitrations, port arbitrations, the read latency. You may not really understand every parameter that I'm mentioning here. That's okay. I'm just trying to give you some kind of a hint as to what are some of the parameters that are typically looked at. And like, I mean, people just play around with different like pipeline depth. They will increase, decrease, run different inputs and see whether this is really giving me the required output. Even if it is giving, can I reduce it and make it optimal? So those kind of a lot of experiments to and fro. I mean, they're done, and finally you sign off on a kind of a final set of parameters. Right? So then I just want to introduce you to one open source simulator. I mean, this is called GEM'22. It's very popular in academia as well as industry for doing microarchitecture analysis. Yeah. So this is a completely open source simulator. So you can use it to build the complete system. So GEM'22 can operate in full system simulator mode. It's called an FS mode, where you can build the whole system. Yeah, and then the operating system, both are there. So it's basically the hardware plus the software aspects you can cover. Or you have something called as an SE mode. This is called emulation mode, where only the operating system calls are emulated. Yeah. So this works like that, and it's primarily written in C++ and Python, and the popular the micro architectures are supported like Alpha, ARM, x86, MIPS, etc. GEM'22 is modular and extensible. So what it means is everything is open. You can take it. If you have your own device to model, you can model it, integrate this with this, and do your runs and get this. So this just wanted to introduce you so that if you have some projects and other things, you can take a look at GEM'22 and learn from this. Yeah. So Umesh has already mentioned about this. I'm just kind of rephrasing this in the context of the architecture analysis. So the basic skills, what would be required are the C++, the computer architecture, system on chip architecture, yeah, and then the system C and TLM2. System C is basically a kind of a C++ library built for the specific use case of modeling, yeah. So if it is good to have, I mean, even if you don't have it, it's no issue. But if the other things are more necessary, scripting languages like Python and Perl and stuff like that. So if you have them, I think they are the essential things with which you can really get started. So that's a short presentation I had. I mean, we are open for some questions. A few of them now, I think, as Umesh mentioned, we can have more questions at the later stage. I mean, if you have some few burning questions, you want them to be answered. Yeah, it's open.
I just wanted to know that these technologies you're talking about, right? So did they in the pandemic, or were they like that prevalent before as well? So because of COVID, did they increase a lot?
No, sorry, I think I missed few words. But are you saying this invented during the COVID
Not invented,
time?
like the usage did the usage increase a lot during COVID, or?
Oh no,
in my experience at least, most other technologies, the simulation software, like for our college use at least, simulation software increased a lot during COVID. So were these problem before or?
Okay, so I think my view is, I mean, there's nothing to do with COVID. I mean, this is more to do with the complexity that Umesh was mentioning earlier. The number of transistors are becoming more, and the complexity of the IPs are becoming more, and the input itself is very complicated. I mean, it's very difficult now to kind of have a paper-based design and get it working. So that's because of this primarily. Yeah.
Okay, thank you.
Anyone? Yeah, I think one more question we may take if you have anything. Yeah. No. So otherwise, just a one word, final word from my side is it's a very interesting area. I mean, it's like you can imagine you are kind of architecting, building a new system from the scratch. You are kind of building around and you're working as an architect. So I think it's a really exciting field. I mean, with a lot of, a lot of exposure, and you are creating really a cool stuff. Yeah. So if you are interested, please do dive deep into this. Yeah. Thank you. Yeah. Umesh. Yeah. That's all from my side, Umesh. We don't hear you, Umesh.
Okay. Yeah. Yeah. So thanks, Aravinda, for the presentation. And, so now we can move on to the next presentation, which is by Shabarish for the virtual prototyping. So Shabarish, maybe you can share your screen.
Yes, Umesh. Can you see my screen?
I think so. Can you share some presentation? Then we can see.
Yeah, I shared
Yes.
it.
No, presentation we cannot see yet actually.
I have stopped from my side. Or let me just...
Is it visible now?
I mean, we can see the audience actually, but we cannot see the presentation.
Okay,
I don't know
let me
whether
do
it's
it
your
again.
screen which is visible or what.
No, I'm doing entire screen only. So
Okay,
try
so
again.
have you opened the presentation as well?
Yes, yes.
So that's not yet visible actually.
Now?
No, no.
Is it visible now?
Not yet. Maybe you can try to share one presentation itself instead of sharing the entire screen also.
Yeah, I tried that also. Share only.
Maybe you can try, otherwise I can share from this side and you can speak from there. That way.
Can you see now?
No.
No, Shabarish.
Okay. Maybe you can share, like someone can share it.
Okay.
So
So let me share it once. So yes, so can you see my screen?
Yes.
it's
Yes,
blank
Yes.
to me actually.
1 minute, 1 minute.
No, I can see it, Umesh.
Okay, let me rejoin then. I think it looks like some issue with my end. For me, it's showing blank screen.
Okay, so in the meantime, maybe shall we start with Bhavna's presentation then or what?
Yeah, that should be fine.
Okay. Maybe I'll start with my presentation then.
Yeah, sure.
Yeah. Mm. Please let me know once my screen is visible.
Yeah, it's visible, yeah.
Okay. Yeah. So, hi, good evening, everyone. So, I am Bhavna Aggarwal, member of consulting staff at CircuitSutra Technologies Private Limited. So today I'll be talking about high-level synthesis. This word has already been introduced by Umesh in his presentation earlier. I'll be talking a little bit in detail about this. What is high-level synthesis? Okay. This would be the agenda of the my talk, where we will be covering about the basic introduction, what is the need of HLS, what was the traditional RTL design flow, how has the traditional flow changed using high-level synthesis, what are the benefits, and the HLS tools available in the industry. Then some sites to start learning, like everybody would have the curiosity from where to start learning about this new technology, these domains and all. So I'll be also sharing some sites, some links, and then final question and answers. Okay, so coming to introduction. High-level synthesis can also be called as C synthesis. Okay, so it is like an automated design process which will take a higher level abstract behavior specification of the design, digital design, and translate it to an RTL structure. RTL means register transfer level structure. That is the hardware structure. Okay. I know today the audience might be a hybrid of software engineers and electronics engineers, computer science engineers. So these C++ behavior specification might be known to the computer science engineers, but the RTL structures, the hardware designs are familiar word to the electronics engineers. Okay, so like at a first glimpse, I'm sure it might be appearing to all of you that high-level synthesis is like a new language or a new methodology that you might need to learn. But it's not that so. That's not true. It is actually trying to bridge the gap between the hardware and the software domain. Okay, there are many semiconductor industries that are trying to design their custom SoCs for emerging domains. We are very much familiar with the domains like vision, speech, artificial intelligence, deep learning, machine learning, etc. Okay, so many semiconductor industries are trying to design the custom SoCs, system on chips, in these domains. And also like these companies already have the software algorithms available to them, readily available. So in these domains, a lot of algorithms are already available as software implementation. Like, for example, I'll just take an example of Facebook. Facebook already has an image processing algorithm, software algorithm available. But in order to design an SoC, either it will have to write the hardware from scratch, or it could leverage the available implementation, software implementation to design the RTL, and that is where HLS, high-level synthesis, plays the role. Using a high-level synthesis, designers can leverage the available software implementation to develop the hardware, okay, instead of developing it from the scratch. This is how the traditional RTL design flow looks like. I'll not go into detail about each step, but the first important step is the first step, which is the HDL description. HDL description means defining the digital design in a Verilog or a VHDL format. Okay, this is the very much important one. Okay, this is the first starting point of a RTL design flow. How the earlier engineers used, means the semiconductor companies used to develop a hardware using HLS. We have introduced a new tool which is called as high-level synthesis tool. Okay, that will take the input source will change now. The input source is now a C, C++ or a system C behavioral description. The input source and the high level synthesis tool will transform this behavioral description to the Verilog code, Verilog or VHDL code, and the other steps will remain as it is. Okay, so we have just leveraged the available software implementation to develop the HDL description. Now what we can see that the RTL implementation from this higher abstract description will reduce the effort by almost 10 times. Means the engineers will have to write almost 10 times lesser code. And also these C, C++, these languages are very from simulation point of view are quite fast. So the simulation, the productivity also increases by 10 to 1,000 times. Again, already mentioned that there is already C, C++ implementation available to start with. Okay, so for the same functionality, like if we have the same functionality, same behavior, using high-level synthesis tool, the designers, the RTL developers can develop different target hardwares, okay, depending upon the use cases, like low power, high power, small area, okay, depending upon the target areas. So same functionality, but different hardwares, okay, depending upon the target use cases. Also same functionality, but depending upon the different technology, a different hardware. It could be an FPGA. Using HLS, we can develop an FPGA. We can develop an ASIC, which can be based on 19 nanometers, 22 nanometer, 10 nanometer technology. Okay, here the designer is just focusing on implementing the functionality rather than on the micro architecture level details. So we see here that the same using high level HLS, the implementation has become much more easier. Okay, I'll talk about this benefits more in detail. Okay, so in terms of design, how HLS tools are helping, it allows us to focus on designing the core functionality, not the implementation details, not the architecture details. Okay, it also it has also made it easy to explore different architectures, as already mentioned, on the basis of the different target use cases. Using the same implementation, different target architectures can be developed. So it can easily evaluate the algorithmic changes. A minor change in the algorithm can help you develop the RTL. Okay, so a lot of effort won't be required. A minor change in Verilog code or a VHDL code requires a lot of effort instead of making that same change in a C, C++ implementation. Then it can easily generate the memory, and using the HLS tool, the memory, IOs, the host interfaces, pipelines, handshake, arbitration logic, etc. Everything is very easily taken care of. Also, it retargets for different hardware constraints. Already mentioned that 10 nanometer technology, 19 nanometer technology. So different hardware constraints can be very easily targeted using HLS tool. Along with the design, verification is also very much important. Unless and until an hardware is verified thoroughly, we cannot say that it's a true hardware. Okay, so how HLS tools will help in verification? Okay, firstly, HLS tools makes it easy to debug and test the functionality of the input description, because the input description is nothing but a higher level abstract behavior description in the form of C, C++ or system C. Also, the verification simulation would be faster and free. Then for this, say like C, C++ algorithms are already available. Likewise, their test benches, C++ for those algorithms, the test cases would also be available. So the test suite is also available. The same test suite can be reused for RTL verification using high-level synthesis tool. Then also these tools provide means for code coverage and functional coverage, which is much more meaningful and easier to achieve. Talking about more benefits to the RTL developers, to the hardware developers, in terms of view and analysis, the RTL developers can view the area utilization, the surrounding logic, the memory map, loop structure, data flow, the clusters, and all. So it gives a complete architecture view for the RTL developers when they use an HLS tool in order to develop a hardware. Okay. So these were all, till now I was talking about the benefits. Now let's talk about some of the tools that are available in the industry. Okay. The tools are all of these tools that are mentioned here are commercial tools. Okay. So there is a Catapult by Mentor Graphics, which is now a Siemens business. Vivardo HLS by Xilinx, Stratus HLS by Cadence Design System, Symphony C by Synopsys, HDL Coder by MathWorks, HLS Compiler by Intel, and many more. You can Google it, you'll get a lot of list. Okay, and so then again I'm mentioning the input source to these tools would be a C, C++, System C, or a MATLAB code. You can very highlightedly, I have mentioned here, a synthesizable subset. What is a synthesizable subset? That is, we'll not go deeper into it, but in a brief, I'll explain it. A synthesizable subset means a logic that can be synthesized. For example, in C, you cannot directly use double. There is a subset for double data type, okay, that needs to be transformed. A designer needs to understand that, the synthesizable subset, and accordingly change the available algorithm. Okay, so these were about the tools available. These are some of the sites from where you can start learning about high-level synthesis. There is a course available over Udemy, even some videos over, on YouTube, and even some YouTube course provided by Intel. This is where you can start from. So any questions, anybody?
Hello, ma'am.
Hi. Yes.
So I just want to know that how efficient and optimized are these high-level synthesis tools? Like if some person or some company want to design a very high-tech processor or chips type of thing, so what will they prefer? Like these HLS or traditional RTL design, or mix of both type thing?
See, we are talking about high-level synthesis because it is now the preferred form that the organizations are taking up. Okay, and there are a lot of commercial tools already available that is helping in these areas for the development of the processors, for the chips, for the cores. Okay, so absolutely means they have not, the industries have not 100% absolutely transformed to HLS, but they are in the phase of shifting. They are in the left shift process. They're in the left shift process where they're shifting from the traditional flow to the high HLS flow. Okay, it always takes some time to leave the traditional format, traditional flow, and adopt the new one. And this is why we are talking about emerging technologies. And many industries have already adopted it. That's why there are so many commercial tools already available. Did I answer your question?
Yes, yes. Thank you, ma'am.
Welcome. Anybody else? Any question? Okay, so shall we move to Shabarish presentation?
Yes, so I think we can move to Sabrish's presentation. So Sabrish, can you try to share it now?
Yes, yes. Can you see now?
Yes, yes, we can
Yes.
see now. Yeah.
Okay, okay. Yeah. Hi everyone. My name is Shabarish. Today I'll be talking about virtual prototype. It is one of the widely used use cases of models for free software development. And today's agenda, what we will see is like we'll see what is a virtual prototype, why they are used, and what are the advantages it has compared to the physical prototypes like FPGA and other things. And we'll also touch upon the abstraction levels and the tools available and the limits and requirements of the virtual prototype. What is virtual prototype? A virtual prototype is an executable software model of hardware system that runs on a host computer. So what it means here is like it's nothing but a model developed using high-level languages like C, C++, so which can execute faster than the RTL simulation, and it is developed functionally accurate so that we can execute the production software without any modification on the virtual prototype. And another benefit is like we get the full visibility since the virtual prototype is developed using the software, right? So using this same software debugging tools, we can put breakpoint inside the hardware blocks and we can see the state of the blocks. So it's very easy to debug in a virtual prototype or virtual prototype compared to the real hardware. And the next advantage we get with this is easy deployment. Since it's a software model, right? So we can easily ship it across the teams in the organization, or we can ship it to our customers. So the next question comes is like, why do we need it basically? So we already have the RTL models, right? So why do we need this thing? So if you see the traditional development cycle, right? So it's very sequential. So first it starts with architecture design. So where the design is finalized and the spec is ready. So once the spec is ready, it moves into the next phase where the RTL engineers they start developing the IP blocks. And the next phase is like once the entire chip is developed using RTL, it goes into the fabrication process. And then we get this silicon, and then the software development starts, which is at the final stage. And if you see the time taken, right, starting from the requirements till the final product, it takes somewhere around 2 to 3 years, depending on the complexity of the SoC. Like if you see, even to develop a medium to complex chip design, right, it takes nearly 12 to 15 months of to develop an hardware, and it requires 9 to 12 months time to develop a software, and 6 to 9 months to validate the software and verify it. So in total, somewhere it requires around 3 years. And the challenge here is, right, so the time to market pressure is, right, everybody wants to release their product early in the market. So there is a chance of getting success, right, whoever releases first their product. So people started thinking about those things, and they started how we can parallelize some of these phases instead of doing it sequentially. So then they came up with this something called like virtual prototype, where we can develop the complete SoC in a software model, and so that the software team can start developing without having the dependency on the final chip. So instead of doing it sequentially, so what we will be doing, like once the spec is available, right? So the virtual platform development will start in parallel with respect to the RTL team. So somewhere in this, in the mid of phase 2, right, the virtual platform will be ready so that the software development can start. So by doing this, we almost gain around 6 to 1 year of time to release the product. And it also reduces the risk of system integration since we already verify the software on the virtual platform, right? So we just need to run the same software and the final chip and validate, and then we can. It's good to go for the final chip. And coming to the advantages, right? The first advantage, right? It shifts the start of software development, and the second thing is deterministic. If you take the hardware, right? So in hardware, all the blocks are runs in a parallel. So it is now you don't get the same result every time you run an application on hardware, right? So it's very sometimes it's very difficult to debug the corner case bugs on the hardware. Coming to the VP, right? Since it's a software, so we can get the same behavior every time we run the software on the VP. So that is the advantage we get by using VP. Another advantage is if you take the hardware, right, you can see on the states only on the boundary point, or you can, if the SoC has some hardware like a trace component, right, you can get the trace. But it is very time consuming, and it's very difficult to identify a problem and fix it. So coming to the VP, right, you can pass the simulation, and you can put breakpoint at the exact point where you need to get the state and see what is happening in the system. So in that way, it gives it's more easier to debug an issue in VP compared to a FPGA or ASIC chip. And the next advantage is, right, so we can try some negative kind of scenarios in a VP where without damaging the hardware. So if you are if you are developing in a automotive product, right? So if you want to test your ABS and all, right, it's very difficult to do in the real final product. So whereas in the VP, we can give the inputs of such scenarios to the VP, and we can see how the model is behaving in those scenarios. Whether all the functions are behaving properly in case of this kind of negative scenarios. The next thing is abstractions. So the main difference between RTL and VP is, right, so we don't model the hardware at the RTL level or cycle level. We model at a very high level where we model only the components which are required to run the software, and which is functionally accurate, and it has register accurate. And timing is somewhat loosely timed, so it is not cycle by cycle. So we model timing at the block level or at the transaction level. So if you see this, these are the IP blocks. Typically, you will see in a VP, you have an interrupt controller, you have a CPU, you have a memory model, and there may be other peripherals like USB, Ethernet, Wi-Fi chip, all those things. So basically, we model what is required for the current software development team. So we usually develop this VP in phases, since we start in parallel with the RTL design, right? So depending on the software requirement and their priorities, we ship this VP in phases. So initially we start with basic components like CPU, memory model, and bus model, and slowly we start the next models, whichever the software team has the dependency. So in this way, there is no dependency for the software team on the RTL team or final chip. And depending on the use case, right, we can trade off between the accuracy and the simulation speed. There may be a use case where you need to evaluate the performance and IP model. In those cases, we need to model the timing behavior accurately for those IPs so that you can capture the performance of those IPs required by the software. And depending on that, you can mismatch the components, where you need the IP components to be accurate. You can have a detailed implementation for the timing. So in the other rest of the IP blocks, it can be a simple register and functional accurate. And you can also prove the equivalence of specification by using the BP and hardware. And this will serve as a golden reference for the final chip, right? So you can use the BP as a golden reference for your final chip to run the same test suite on the BP which you used. It can be run on the final hardware to verify the equivalence. So if you compare the simulation speed, right? If you take RTL, right? RTL is cycle accurate, so it is very slow to simulate RTL compared to a virtual prototype, which is like much faster than the RTL. And even coming into the virtual prototype, right? There are two possible ways to do it. One is to have a instruction set simulator for the CPU, where we have an actual instruction decode, execute kind of thing cycle. And the other approach is to have a CPU using the host compiled thing, so that what it means is, right, the final software, right, you compile it for the host machine, and then you run it on the prototype. Basically, it avoids the conversion part. Example, right? So in the target SoC, you might have an ARM CPU, but whereas you will be doing the development on a x86, right? Instead of having a decoder, what you do is, right, you compile it for the host machine for the software, and you create a wrapper around that CPU, and you connect it to the virtual prototype. So in this way, you can improve the simulation speed. Next topic is generic test environment. So this, as I mentioned earlier, the same test suite which you use to run on the virtual prototype can be used by the physical chip as well. So there is no change in the environment as per with respect to the verification team, right? So they can use the same tools which they use to verify an actual chip, right? The same environment can be used with the VP as well. So this VP will serve as an abstraction layer for all these debugging tools and the test suite. Interface to signal generators, digital I/O. So what it means is, right, so if you take your host development, right, you have a USB interface physically. So what you can do is, right, you can create an adapter in the host OS, right, and you can plug it into the VP. So in this way, you can connect a real USB drive, and it can be detected on the VP. So this kind of things are possible by using the virtual platforms, where you can verify with the real-time user inputs and all. The major drawback with VP, right, what it is like, it increases the additional cost. Like, you need additional resources to develop the VP in parallel to the RTL team, and you'll be needing some commercial tools to simulate this VP, so that you get the traces and the better debugging capabilities. And the other thing is, right, you might face is like you have incompatible interface between different tools. Like maybe some teams are like using different tools, and some other teams are using different tools, right? It becomes very difficult to integrate those IP models which are developed using different tools. So that is one drawback. And the other thing is, like, it takes a very high effort to integrate models of different vendors. So this is a case where you are getting an IP from different customers, and you want to integrate it inside your in-house SoC. So in those cases, if it doesn't follow the standard, there is no standard interface, right? So it takes time to understand and integrate those kind of models. And these are the list of freely available tools and commercial tools. And System C. So this System C is nothing but a language. It's a library of C++, and Accelera has a proof of concept simulator provided with this System C standard specification, right? And we have a Kimu, which is an open standard. It has a lot of platforms available for different kind of SoCs, where you can quickly get started for your exploration kind of thing. And coming to the commercials, we have something called as virtualizer, provided by the Synopsys, and from Intel we have something called as Siemens. Any questions? Hello.
So we can take up any questions if anyone is having on any of the presentation so far. Okay, so I guess we don't have any
We can
questions.
have the question. We can have the questions mailed as well. If they have any questions later, we can have them mailed to you and then you can answer them.
Yeah, that's also fine. I mean, you can drop a mail
Yeah.
to us if you have any queries further here. Okay, then thanks everyone for joining.
Thank you, everyone.